What would happen if we dug a hole straight through the Earth? Imagine embarking on the most ambitious excavation in human history, a venture to bore a tunnel from one side of our planet to the other. The Earth's radius stands at a daunting 6,371 kilometers. This thought experiment not only stretches the imagination, but also probes the limits of our scientific and engineering capabilities, teasing at the mysteries of physics and Earth science. Join us as we embark on a journey to the center of the Earth. To imagine digging through Earth, first, we need to understand what we're digging through. Let's start with the outermost layer, the crust. This is the solid rock layer you're standing on right now. It's relatively thin compared to the rest of Earth, ranging from about 5 kilometers under the oceanic depths to 70 kilometers under mountainous regions. Despite its solid appearance, the crust is actually like the shell of an egg, brittle and broken into pieces known as tectonic plates. Diving deeper beneath the crust lies the mantle. This vast middle layer extends approximately 2,900 kilometers downward. It's not molten, but it is viscous, almost like an extremely thick paste that slowly moves. These movements in the mantle are what cause the tectonic plates of the crust to shift, leading to earthquakes and volcanic activity. Next, we reach the outer core. This layer is radically different as it's composed of liquid iron and nickel. Stretching around 2,200 kilometers thick, the outer core is a swirling metallic sea that generates Earth's magnetic field, an essential shield against solar radiation. Finally, at the very center lies the inner core. Solid despite the intense heat, the inner core is made primarily of iron and nickel. It has a radius of about 1,230 kilometers. The temperatures here can reach as high as 5,700 degrees Celsius, similar to the surface of the sun. With each layer, the challenges and temperatures rise, complicating our imaginary journey. What role does gravity play in this subterranean scenario? Imagine an object, say a ball, dropped into a tunnel bored straight through the Earth. As it starts its journey, gravity from the Earth's mass pulls it downwards. But here's where it gets interesting. As the ball moves closer to the Earth's center, the gravitational pull doesn't remain constant. Instead, it decreases. Why, you ask? Well, gravity is a force that depends on two main factors: the mass of the objects and the distance between them. As the ball descends, more and more of the Earth's mass is actually above it, not below it. This change in mass distribution causes the gravitational pull to weaken. By the time the ball reaches the very center of the Earth, the pull from all sides is equal, leading to a sensation of weightlessness. Gravity at this point is zero. But the journey doesn't end here. As the ball ascends towards the opposite side of the Earth, gravity begins to increase again, pulling it towards the new surface. Thus, gravity isn't just pulling us down, it's dynamic and changes with depth. As we dig deeper, the conditions become increasingly extreme. Imagine venturing into a realm where the thermometer soars to readings reminiscent of the sun's fiery surface. Yes, we're talking about temperatures that can reach up to 5,700 degrees Celsius. It's a scorching reality down there, akin to being in the heart of a star rather than our own planet. But it's not just the heat that would challenge the most audacious of diggers. The pressure, too, mounts to levels hard to fathom from the surface. Picture this. At the Earth's core, the pressure is about 3.6 million atmospheres. To put that in perspective, it's as if 3.6 million blue whales, each weighing around 180 tons, were piled on top of you. Under such extreme pressure, every material that we know of behaves in ways that are wildly unpredictable. These outlandish conditions render our current technology virtually useless. The materials and machinery that serve us well on the surface or even in the upper crust would stand no chance deeper down. Metals would melt or deform, electronics would fail under such intense heat and pressure, and any attempt at human presence would be instantly fatal. The deeper we go, the closer we get to conditions that are utterly alien to our surface-dwelling experiences. Imagine a world where our everyday rules of physics and material science bend or even break under the strain of Earth's inner chaos. It's a fascinating yet formidable thought. What kind of technology would we need to overcome these challenges? Diving into the depths of Earth isn't just a matter of digging, it's a monumental engineering and scientific endeavor. Imagine materials that must not only withstand extreme temperatures that soar above 1,000 degrees Celsius, but also endure pressures that could crush conventional machinery like a tin can. First, consider the robotics involved. These aren't your average factory robots, They would need to be a fusion of the most advanced materials science and cutting-edge engineering. Picture robots coated with a new breed of heat-resistant materials, perhaps a composite developed from graphene and silicon carbide, capable of operating in conditions that would melt most metals. Next, think about the pressure. The deeper you go, the greater the pressure. Any technology deployed in this environment must be adaptive to immense pressures. This might involve materials currently on the cutting edge of research like metallic, hydrogen, or amorphous metals, known for their exceptional strength and elastic properties. Then there's the challenge of removing the excavated material. It's not just about digging a hole. It's about continuously transporting tons of earth to the surface. This would require a highly efficient, perhaps even autonomous, system of conveyance. Maybe a series of ultra-strong elevators powered by a network of superconducting motors, or an innovative mass driver system. And let's not forget about stabilizing the tunnel. This could involve a self-assembling architecture using smart materials that change properties based on environmental cues, ensuring structural integrity in real time. Our current technology falls short, but it sparks the imagination about future possibilities. Our journey through the Earth comes to an end, but the wonder doesn't stop here. Imagine for a moment that we could actually tunnel straight through the Earth. We've delved into the fascinating layers of our planet, from the crust to the core, each layer presenting its own set of extremes from solid rock to molten metal. We've seen how gravity would behave in such a scenario, pulling us towards the center and then changing direction as we pass the midway point of our theoretical journey. The extreme conditions inside the Earth, with temperatures and pressures that dwarf anything we experience on the surface, pose monumental challenges. Even with hypothetical technology far beyond our current capabilities, the task remains daunting. These extreme environments, however, offer us a unique window into the processes that shape our planet and influence everything from volcanic activity to magnetic fields. Though a tunnel through the Earth remains a fantasy, it invites us to explore and appreciate the incredible planet we inhabit.
Don't forget to like, subscribe, and share this video. That's all for Nifty Narration.